thank you very much. Well, I work in the area of mathematical analysis, in some sense also numerical. Especially, I have worked a lot on the special function and orthogonal polynomials, and in some sense also in the last years, but 20 years ago too, in the fractional calculus. Now is, I think, too much talk about fractional calculus. Here there are some items related to them, but the aims of this, the core of this seminar, is how we can make generalization by using orthogonal polynomials and special function for the wide family of Heat-Eqn. This is the idea, so that the title is Special Polynomials and Function in the description of various generalization of Heat-Eqn. Let me see the abstract. Is exactly what I said before, and in particular I would like to outline that we will discuss of pseudo-hyperbolic function that could be presented in terms of the Hermite polynomials that I think are the stones of every construction that you want to do in the mathematical analysis, especially for construction relation relative to differential equation of things like that. How we can organize this presentation? We give an introduction on where we want to work on the Heat-Eqn family, and that means in the D'Alembert and Fourier type, which are the tools that we use, and we will use again pseudo-hyperbolic function. Then we'll do some consideration in different future investigation, and also we can discuss on fractional equation that we usually call fractional diffusive equation of high order. Well, very interesting the application of this equation, you know, and then maybe this could be in some sense useful to make advances also not only analytical but also numerical, because some of the generalization of this Heat-Eqn or some of this family could be not solved in analytic form. Let me start so with the presentation. You will know that the possibility to the concept of hyperbolic function, you want to study equation of this type. Heat-Eqn general, well, M and R are positive integer. Usually the other parameter H usually is real. I have written complex or real, but in general for our scope is real, but it could be useful, it could be easy to extend to the complex case. This is the standard general in some way Heat-Eqn, where we can to manage the parameters, etc. And we will see soon it's possible also to reduce in a different way by reading that as ordinary, but we will see soon. So that start to discuss some special case. When M is equal 1 and the R is equal 2, then we get this. And that means that the Lambert equation. When instead we change the number, the integer, and M equals 2 and R is equal 1, then we have this equation that usually is called Fourier Heat-Eqn. So that we make some consideration about these two equations. That is, we want to study how is it possible to make a representation of the solution of this family of Heat-Eqn, D'Alembert and Fourier Heat-Eqn, D'Alembert wave equation, it's better to be precisely, and Fourier Heat-Eqn, by using pseudo-hyperbolic function, which is the tool that we use. As I said before, there are PD, are partial differential equation, but we can treat these families of equation, each of them by study and consider them ordinary differential equation. That is a standard method of solution in the complicated cases, and then we use in this case for the variable, for one of the variable, to read or treat, as you want to say, this equation are ordinary. Let me go on. Oh my god, what happened? Okay, sorry. Before to introduce the method of solution, or in some sense of the generalization of the solution of the previous equation, let me introduce the tools, the instruments that we want to use for this equation. As we said in the introduction, we want to define some kind of function, exotic function in some sense, called pseudo-hyperbolic function, that, you know, are represented in this way. There are a long story about this point. They come at the second half of previous century, and some of the representation has been done maybe 40 years ago from one of my professor here in Rome, that is Paolo Emilio Ricci. There was a very nice paper about this function, that the application of this are useful in the applied physics for free electron laser. So that is a very, very nice generalization of the hyperbolic function. Anyway, these are the form, the explicit form. These are rho of L, which is the representation. That means we can read in this way. But let's go on and arrive, of course, to the very famous Hermite polynomials that we can always use in every context. They always help us for any scope. Here what we have the second two variable n order Hermite polynomial that usually are called Gould-Doppler type. That is a paper of in fact Gould-Doppler of the 60s of last century, and this we give directly their explicit form. It's very easy to remember that the generating function is the exponential of xt plus yt squared. This is the standard Gould-Doppler polynomial that in some way are the generalization of the famous Hermite of Campé de Fourier type of the 19th century. Anyway, put this polynomial in the representation of that function, and then what we get? We get this expression that gives us the possibility to read the explicit form of the hyperbolic function in terms of Hermite polynomials, of course, of a specific index kr plus j. But it's just a computation, is not interesting to do. Well, what we do now is possible to use that pseudo-hyperbolic function written in terms of Hermite polynomials to solve in some sense family recognized to belong to D'Alembert equation or Fourier equation. Yes, of course, yes, we can do. And it's also to know that for this, for instance, if we treat a trivial differential equation, ordinary differential equation, it's very easy to note that is possible to define the translation operator, or if in some sense of the operator that give us a step on with the function, we can obtain for, of course, an analytic function in the neighbor of the origin. This is a standard, of course, we are talking of Taylor series. If we define this operator, then we see that we apply to this kind of function, we have this translation. And this is what we want to use as technique, in the sense we have an equation, we have the pseudo-hyperbolic function in terms of Hermite polynomials. Then we use the theory of translation, or also called shift operator, to apply this operator to solve the related equation. In which way? Well, here is some generalization of this. If I have a second order derivative, we obtain this exactly. The Hermite polynomial is a very nice exercise to do, because let me spend a few words about this point, because I think it's a good exercise. If we go the explicit form of this member, then we have to note that we have to put in the Taylor series the derivative of order 2. Then we have to remember that if I use y, I have not problem. But if instead of y is x, then I have to check if the two exponent of this operator commute. Otherwise, I have to compute the commutator. So that this is it seems simple, but you have to be really careful when you do this operation. Here is easy. I mean, this obtain an action of g of x that will be g of plus lambda for first derivative. Then with other computation obtain this. Instead, in fact, sorry, you can see this operation at works. Are very interesting, this theory of operator. I mean, is maybe 100 years old, but it's very interesting with all the connection that has with orthogonal polynomial. That what I say until now. We have seen the pseudo-hyperbolic function. The paper of Paolo Emilio Ricci was 78, in fact, more than 40 years ago, I remember. These are some of paper that we did also with supervision of Paolo Emilio Ricci. This one for the computation. I just to write the basic book on the Hermite polynomial that I have cited before, the Appel-Campé de Fourier polynomials. The Guldopper paper was of 62, and then for the computation of operator theory, when we talk about commutation, commutator, and things like that, then the book of Miller, Lie Theory and Special Function, is very powerful book for this. But go on, and then arrive to try to solve these two family equations: wave equation of D'Alembert type, heat equation of Fourier type. Okay, there are PD. We start for the first case when m is equal to 1 and r is any positive integer. Then we obtain this form. To write a general solution, so that we can formally write the equation in this form, where we have written in some way this kind of operator is exactly the partial derivative. Now we do what we have seen, treating the operator as constant. Then we can solve directly the we can solve directly this equation as an ordinary differential equation, because in this case we are treat the variable x as a constant, and then we have also put that the initial condition y equal to 0. We have a simple linear first order differential equation. Is linear, we have the exponential, and then what happened? We have seen before the powerful of the exponential operator of translation or shift operator give us the solution, in this case for g x plus ht. We just to make this translation with exponent to argument. Okay, now make a further extension, and then with what we have done, what we have said before regarding the pseudo-hyperbolic function, I can do exactly the same when make a generalization, when I'm looking for the general case. I use u of xt, we write this by pseudo-hyperbolic function applied on the function g. I remember always g of x is an analytic function. Okay, we are studying the context of real number, is better to have. And then, sorry, and then we have this expression of the function. This is the general solution of the case m equal to 1, r equal or greater than 1, r equal to greater than 1. And this is exactly the classic D'Alembert solution when we choose simply r equal to is inside this. I don't know if it works, sorry. But we can do more. We can use this by already introduced. We can observe that since they satisfy this equation, the Hermite polynomials, again, we can read this equation as ordinary because we can consider constant the variable x, and then again the initial condition is y equal to 0. Again, we have this, and immediately we have the same situation for this other solution. And this other solution is for the case m equal to r equal 1, that is exactly the solution of the other family, that is Fourier Heat-Eqn. So, if you want to go on in this case, then not only we can, I mean, the theory, this theory that we have showed now is in general for all analytic function in the neighborhood of the origin. This is the condition for J. But maybe if you want to be less general and we want to suppose that the function is instead a polynomial expansion, then we can do more. And then we construct this function in this way as a much more easy function to see, but give us a lot of benefits to represent them. And this is give us the possibility to talk on a principle that will be in some way exploited and generalized 30 years ago from our group in Rome with with Paolo Emilio Ricci, with Pino Dattoli, in few part from myself, and this is the possibility to classify the orthogonal polynomial, not only orthogonal, some class of polynomial, treat them as monomial, that the name quasi-monomial. And okay, these are other some generalization about this point. I start from the Srivastava Manoja book. It's a treatise on generating functions. It's very, very important. Here is a short note on the part of the equation that you see. Here is a not published paper of 20 years ago when we work with Pino Dattoli. And this is a Xiu book on the algebraic approach that we have seen in some way, how we can treat PD as OD, which are the condition to put. We have talk, I mean, soon, but it's not trivial to say, okay, I treat a PD as OD. It's not enough. It's not trivial to say, okay, I consider one variable as constant. No, you have to be careful. You have to know where is the domain of the variable, and then you can discuss. Okay, but the wave D'Alembert equation, Fourier Heat-Eqn are well known, and there can consent us to do this. Now, this part I want to go faster. I don't know how many time I have, because I would like also to spend a few words on the fractional possibility, generalization fraction. This is interesting from another point of view. This is interesting because give us the possibility to explore a generalization of Hermite polynomial where we use the parameter m, that is an integer, and it is interesting because they could be introduced directly on the translation or shift operator. And this is very interesting because it is not enough to start with a generating function with explicit form with difference equation or when directly with hypergeometric function. But let me say a few words historical point of view. When the Hermite polynomial how the Hermite polynomial are defined as a solution of differential equation. They are solution of this kind of differential equation when in the beginning of 19th century, the end on 18th century, there are the problem to make the approximation theory by using some classes of polynomial, and then the solution to make the transform from a difference equation to a differential equation was the method of generating function. So that if I want to define an Hermite polynomial or a Chebyshev polynomial, for instance, I have to go directly there. Now, after more than 200 years, it's possible to define and introduce them in very general way, also by give directly the explicit. Let me say that I think it's much more elegant this part that is with the operator applied to analytic function. Is my opinion, of course. Let me go fast. We do the same equation. We do the generating function. We find everything related to this family of polynomials. But which are our scope? Our scope is to understand if is it possible to make a generalization of that family of Heat equation with this way, and then it's okay because this operator works in the same way I give this polynomial. This operator works in the same way on analytic function and give this expression. So that, well, we have the solution of a general Heat equation of the Lambert type where m now is greater than 2 and r is greater than 1. So we are very general. Again appear the pseudo-hyperbolic function. Again, they arrive in terms of the Hermite polynomial. These are cited only two of my papers, but there is a lot of in literature about, well, not a lot in this sense, a lot by using that family of polynomials of Hermite type. Let me go to the end with I said at the introduction. I am in the time, yes, I'm 30 minutes, so maybe it will be a discussion later that I prefer. What is this equation? Yes, is an Heat equation in some way? Well, it depends on this order. Which kind of order we want to say? It's not an integer now. It's a real number between 0 to 1. Okay, what we can do about this? Let me say something about fractional derivative. Fractional derivative as a funny story comes recently from an Italian Caputo, that is the Caputo derivative, that is 30 years old. I have met him some months ago, and is not a mathematician, is a geologist, study geology, and he used this in the fractional calculus in the fracture. This is the story. But 200 years before, or 150 years before, because it was the beginning of 18, the first idea, of course, was from Cauchy and Liouville. Again, I mean, Cauchy gave a large contributor to differential equation, ordinary, partial. Then, of course, if you start with integer, why not to start on fraction? So there is a formal definition of fractional derivative that is called the Cauchy-Liouville derivative. the Caputo derivative is much more useful for computation. But we see another approach that comes from Cauchy-Liouville, but as the operator of kind of this. Again, always Hermite polynomials. These are usually called exotic Hermite polynomial. There are in some way defined for a parameter not integer, a real parameter. That's the reason of gamma function here. Well, where I have seen before these polynomials, there are in some way seen in the different context. But a very good friend, Alfred Wunsch from Humboldt University, that I meet him maybe 25 years ago, present in a conference this family of polynomials. You can recognize the same structure of the other polynomials. Well, instead of mu was m, and then you have, of course, some modification in the positive part of that. But anyway, I mean, I make an act of faith. Accept, please, that this polynomial exists. It's possible to define. I'm sure that we don't have time to do, but we have a generating function. We can find, in some sense, an OD that will be solved from this class of polynomial. We can recognize some recurrence relation, etc. What we can do with this kind of Hermite polynomials? We replace an equation, and then instead of use integer derivative, we use real derivative. I mean for order. And then what happened? First of all, in the same recurrence relation solved for the standard, if you want to call the standard, or better, integer Hermite polynomials. Again, I read with x constant. I put y equal to 0 as initial condition. I solve the equation in this way. But what I have done, I have exactly give the solution of a fractional diffusive equation that has this form. Moreover, we can do more. We can recognize that this function is an analytic form giving from a translation operator of this solution. But this part is very, very interesting for future investigation. Why? Well, because if you are in some way expert on special function, you know that everything is possible to combine to obtain hybrid orthogonal polynomial, hybrid function, whatever. So that it's not a secret that we can represent Bessel function in terms of generalized Hermite polynomial, and we do the same. There are a lot of hybrid polynomials. My opinion is that you have to be careful to do because otherwise you do let me say, a stupid exercise. If you want to add hybrid families, you have to do some generalization what you need to generalize as a solution of a differential equation. Otherwise, is an exercise that are not useful. Are useful as exercise. So that it's possible, from my opinion, to try. That the reason because I have organized the talk in this way for a mathematical physics equation as D'Alembert and Fourier. Just exactly to underline that it's possible to make modification on some function and then obtain something that is useful for our for application. In this case, for that equation. Let me left last few reference. again, this is what I said before. It's possible to compute or represent, if you want, Bessel function with Hermite polynomials. There are a large literature, I think, in this hybrid context, and these are some papers where some of the previous relation are present. Thank you very much. Thank you very much, really.